Right. So this is a kind of weirdly asked question, or it gives a lot of interesting information that you need to work through. But the main idea is we're looking at a swimming pool, some mass of water. We want to heat it by a certain amount, and the best way to do it is by burning a gas. And we assume that the energy transfer during this process is going to be 100% efficient. And we are given some information about the gas burning processes, enthalpy, as well as its reaction equation. So that's the main idea. We have, so I mean, you can read it, it's a very long question. So it says a swimming pool, the water in the pool is equal to 92% of the swimming pool's volume. So, I mean, that of course also means something. The owner of the pool wishes to heat the water from 26 degrees to 33 degrees. And this can be done by combusting propane gas, in other words, burning gas. How many grams of propane will be required to heat the water in this manner, assuming there's no energy loss? And then we're given some information. So pictorially, what this means is we have a swimming pool, right? And there is only 92% of the volume of the swimming pool is water, and we call the water our system, right? And our system is going to receive heat from the burning of propane gas. So we can call this our surroundings. So burning the propane gas heats our system. We want to know if we want to heat our system by a certain amount of temperature, how much propane gas do we need to burn? Okay, so we'll start linking the concepts together just now. The basic idea is we're told it's 100% efficient, or the energy transfer is 100% efficient. So that means whatever our system absorbs must be equal to the heat that our surroundings gives off. All right, so there's that relationship between them. We can use some different notations, so I just can call so we remember what is what. So the system is the water, and the surroundings is the combustion. So let's give it a big name, combustion of C3H8. Okay. And how do we normally calculate heat, or anything for that matter, or how much heat, the heating of a substance in one phase? We would say, well, it would be the specific heat capacity times the mass times the temperature change. So that's how we will know how much heat we require, because we're asked, we want to heat the pool. So our first step is to determine how much heat does the pool need to undergo that kind of temperature change. Okay, specific heat capacity is what's given here. So we have the specific heat capacity. The temperature change, we have that. So it's from 26 to 33, so we can calculate that. But we want the mass of the water, but we're given some information. We're told, okay, that the pool, let me quickly draw a 3D version here of this pool. We're told that this pool, which is, what is it by what, 43, so 43.3, there's a 13.3, and there's a 4.39 all meter, right? So that's the pool's dimension. At the water is actually only 92% of that. So first, we can determine the volume of the water, and then we can use its density to get its mass. So let's write something here that says mass of the water will be equal to the density of the water multiplied by the volume of the water. But how do we get the volume of the water? The volume of the water is going to be equal to 92% of the volume of the pool. So that's 0.92 times the volume of the pool. And the pool's volume is going to be those three measurements multiplied by one another. So it's equal to 0.92 multiplied by 43.3 meter, 13.3 meter, and 4.39 meter. That then gives us a value of 2325.9 cubic meter. And now we have a big task here because our density is given in 1 gram per milliliter. So how many milliliters are there in a cubic meter? Well, we can just start somewhere. So if we want to get rid of, there will be 1000 milliliter in 1 liter, and there is 1000 liter in 1 cubic meter. Okay, so that gives us cubic meter. Volume of the water is this 2325.9 cubic meter. Should have given myself more space. Yeah, you should get a value of 2.325 times 10 to the power 9 grams. So a hell of a lot of water. Right, so that's the mass of the water. So now finally, why did we even do that? I mean, we might have even forgotten about that, but why we did this in the first place is we wanted to calculate the amount of heat the water requires to make that temperature change. So it's the mass, so there's 2.325 times 10 to the power 9 gram, multiplied by the specific heat capacity, which is 4.184 joule per gram per Kelvin, and that is multiplied by the temperature change. So it's 33.3 degrees C. Don't know what I wanted to write there. Minus 26.4 degrees C. So we wanted to get to 33 degrees. We are at 26 degrees. This then gives us a value of, we need 6.71 times 10 to the power 10 joule. That's a lot of energy. It's actually not that much, but it is quite a lot. But I don't think this is a massive amount of water. Like, how many liters is this even? I mean, okay, it's quite a large number of liters, because it would be, okay, that doesn't really matter, but it's about 2.3 times 10 to the power 6 liters. So it's like 3 megaliter of water. It's a massive swimming pool. Okay, anyway, that's my thoughts getting the best of me. So that means the amount of heat the combustion reaction needs to give off. So combust is going to be negative that, 6.71 times 10 to the power 10 joule. I mean, that's what we wrote up here. So we said water, whatever the heat of the water is, the combustion is going to be the negative of that. All right. Now we need some new information. So now we need to know how much heat this combustion reaction needs to give off for us to heat the pool. So now we need to try and relate that to a quantity of propane. And the only thing that we can relate here between propane and heat is propane and the enthalpy. So this tells us that 1 mole of propane per mole of reaction gives minus 2220 kilojoule per mole of the reaction. Okay. You can even write yourself a note that this is delta H naught, not delta RH naught, it's just delta H naught. Okay, so what's our relationship? Well, 1 mole C3H8, 1 mole C3H8 per mole reaction is relatable to delta RH naught, which is 2220 kilojoule per mole reaction. What we have is we have the delta H, so that gets here 6.71 ... times 10 to the power 10 joule. So remember, this one is delta RH naught, and this one is just delta H naught. That's why the per mole reaction gets dropped on that unit. And then we can calculate how much a C3H8 we require. So in other words, what the first line tells us, 1 mole per reaction gives us so much kilojoule per mole. The next line says, what is the reality? So a certain amount would give us then minus 6.7 times 10 to the 10 joule. Okay, and then you drop the per mole reaction in that line. So we cross multiply. That gives us then minus 2220 times 10 to the power 3 joule per mole reaction. Notice that I've taken kilojoule to joule, so that's times 10 to the power 3. In C3H8 is equal to 1 mole C3H8 per mole reaction multiplied by minus 6.71 times 10 to the power 10 joule. Okay, and we just solve for in C3H8 equals then, okay, so I mean you should be able to do this on your own now. You divide by the left hand side, the mole reactions cancel, the joules cancel, and you're left with mole C3H8. So you'll get 30,225, so 30,225.2-ish mole C3H8. And from that we can calculate the mass. So I mean the mass of C3H8 is going to be equal to the number of mole of C3H8 multiplied by the molar mass of C3H8. And that's going to give us 30,225.2 mole multiplied by 44.094 gram per mole is a value of 1.33 times 10 to the power 6 gram. And that's what we also asked for, gram, right? Yeah, we asked for gram, 3 significant figures. And I mean, you can see that's a lot. I mean, that's, for example, that's about 1.33 ton. Not that that's what it's asked, but that's what 1.33 ton C3H8 that needs to be burned to heat that um, swimming pool. And I mean, if you think about it, C3H8 is a gas, so that's going to be a massive amount of gas that needs to be burned. But like I said, that's a massive amount of water in that swimming pool, so it makes sense. All right, so basic ideas here. Heat is transferred from a reaction to a system. We calculate how much heat the system would require, and then we can relate those two quantities. All right.